It's a really long way down to the mantle, and then an even longer way down to the core, of course. So, one way we might investigate this is by drilling down to see. And the Russians did this back in the 70s and 80s. They spent 20 years trying to drill all the way to the Moho, and got maybe a third of the way. Cost incredible amounts of money to do it, and it didn't make it. The hole heated up a lot more than they expected, and there were a lot of other engineering difficulties in trying to get down there. We tried it apparently in next to the San Andreas Fault in California, Cajon Pass, just outside of LA, and I don't know if we were trying to get to the Moho or not, but we didn't get as deep as the Russians did. It's just too much to try to get through there. And then if you did get through it, what materials would you use? On the other hand, there is material that comes up from deep in the earth, from the mantle area, that we can analyze at the surface. Now, it could have changed or it might not have changed. There are whole uh, branches of things like igneous petrologists that talk about how much a sample has changed since it came up. This picture is a picture of olivine, an ultramafic rock that comes from deep in the planet. And you may have heard of kimberlite pipes in relation to diamonds. They also probably come from very deep in the planet. And they give us. You could do your own experimental investigations. I thought this was really cool, but then I'm a geologist and like such things. But this is at Syracuse where they are making their own synthetic lava. So I just thought that was a really neat way to investigate what's going on with. Another important investigation technique is to look at meteors or meteorites. I guess they're meteorites if they actually impact the planet, and they're asteroids or meteors if they're outside of the planet's atmosphere. So, but if we investigate these, we think we're seeing how material looks in the rest of the solar system and maybe the universe. So, um, some of these things we think mirror what the solar system looked like in its undifferentiated state, and some of them look like they might be fragments of other planets, and we can see different parts of the other planets. Meteorites are a really neat material. If you know anything about the Tellus Museum down in Cartersville, they actually have some meteorites, and they do have one, I think, maybe two, but at least one, that are labeled as. Some of the early investigations, and of course still ongoing, dealt with how seismic waves propagate through the planet. And the the realization that wait a minute, they don't just go straight through. So there's refraction going on in the different layers, and then there's differences in the way the refraction happens. You get these shadow zones and stuff like that. That starts to tell us that well, there are different layers in there, and the geometry must be such that we're getting stuff going on with where the earthquake waves show up. If you've had some physics, you can think of this in the same sense of lensing with electromagnetic waves going through a glass lens, where you can start to focus or defocus the waves or the image. Same thing happens with the transmitted seismic waves, so that they refract in different ways depending. The mantle itself is, it's not all the same, it's not all homogeneous. You get the structuring of the upper mantle area, and it's the peridotite rock type consisting mostly of olivine minerals and some spinel and garnet. And you also get diamonds that come from there. That's where we think they originate from, either the upper mantle. Some folks think some of them originate from the lower mantle, and we get some of the chemistry from inside the diamonds. So you get this big upper area, and then you get, remember that we talked about this asthenosphere, different way of labeling things, and that's where the movement can occur. It's right here at the bottom part of the upper mantle. So that's the zone where the shear takes place, where we can move things around and convect currents and stuff like that. Then you get down into a mantle transition area. It's back to a more solid version than the asthenosphere was. It's mostly spinel and garnet mineralogies, and things are changing in the way, they're gradually changing in the way earthquake waves behave in this. Then we'll divide into the lower mantle, and again, stuff is, the earthquake waves are changing some, and you get this. Well, you get a lot of magnesium iron silicate down here, and the phases are important. I'll put a link up with a scientific paper arguing for this. We don't really know much about the lower mantle. All we've got to go on is what we can see from afar with seismic waves, stuff like that. Some folks think that some inclusions inside some diamonds that they've found might be from down here. And then we've got, maybe we can do these experiments to try to guess at what's going on. A neat experimental part is talking about the quartz and stishovite. So stishovite is SiO2 just like quartz is, but it's a different phase. So think back to where we talked about the phase diagrams. This is a totally different, it's not quartz at all, it's something totally different. History of this is like in the 50s, a guy synthesized this artificially in a lab, made this other version of SiO2. So it was a novel thing, but then at Meteor Crater out in Arizona, the actual mineral that he had synthesized was found. And they think as a result of the meteor hitting the planet there and causing such extreme pressures to build up. So you get a change in the way even quartz arranges itself down here because it's so deep and so while we can't really investigate that lower mantle and tell much about it, the core is even more removed from what we can investigate and get to. We try to make models and we try to guess, but just know that this is still up for a lot of debate, and ongoing scientific debate is occurring about what's going on, well, in all the parts, but especially in the core. So from that initial differentiation process, we know that those siderophile, the denser type elements like iron, nickel, and cobalt migrated towards the center of the gravitational well. So our core we think to be, all I put question marks because it's a dangerous term, right? I mean, how much can we really know about how much carbon there is or how much uranium there might be in the core? We are currently modeling it as mostly an iron, nickel, cobalt system. And we divide it into at least into an inner and an outer core. There's a lot of discussion about now how there are probably at least two very distinct crystal zones within the inner core, and so there's like an inner core. But it's simpler to talk about an inner and an outer core, and they're very different, the inner and the outer. So we're pretty sure of the liquid nature of the outer core because shear waves, and we'll talk more about the types of earthquake waves when we get to that unit. But basically these are side-to-side type waves as opposed to compressional primary waves. But the shear waves can't travel through liquids. Compressional waves can. So we know that we get compressional waves passing through the core, but we do not get shear waves. So our interpretation then is that it must be liquid. And then in the inside, there's what's thought to be probably crystalline, maybe multiple phases of crystals, an inner core region. And there's a lot of dynamics. This is not just sitting there, it's doing stuff as well. Crystallizing, changing, heating, maybe growing. There's some indication that the... So that brings us to the idea of the magnetic field of the planet. And it is, well, I'm about to answer some of my own question here, but it is thought to be related to the development of the core. So I am pausing in that because what I want to do here is I want to get you to post in the discussion boards your speculations about what causes our magnetic field for the planet. I mean, it's a huge magnetic field that extends from the core of the planet out into space. What causes that? What generates that magnetic field? What would happen if that magnetic field were to disappear? And what would be different if it had never developed in the first place? Now, in this discussion, you don't necessarily have to have a well-researched position. I want you to start to speculate and start to think about the science. In this case, some of the physics to go along. We call it geophysics when it has to deal with the planet. Start to think about what it could mean. And certainly it's okay to be wrong. I want you to speculate and to try to develop your ideas here. And